Welcome to Let's Get to the Marks. We're looking at the A-level chemistry, paper 2, organic and physical chemistry. This is the 2023 paper walkthrough. Don't forget to pause the video at the start of the question and then unpause when you want to see the answers and the explanation. Really helps if you hit the like. Let's go. Okay, guys, question 1. This question's about the rates of reaction. Figure 1 shows the apparatus used to measure the rate of reaction when an acid reacts with an excess of solid sodium hydrogen carbonate. That's NaHCO3. So they've got some acid in a conical flask. We've got a balance here and weighing scales or a measuring balance there. We've got cotton wool in the top of the conical flask, and we're adding the carbonate to the acid to get a reaction. Now, when different monoprotic, that means one hydrogen, organic acids are used, the rates at which the gas escapes can be used to compare how strong the acids are. So the more gas that escapes in the shortest amount of time, we're going to get a bigger loss of mass, and that's going to tell us which acid is stronger. A timer is started when the NaHCO3 is added to the acid and the mass of the carbon dioxide gas loss is recorded at regular intervals. It's assumed that the change in the mass is due to the loss of CO2. Suggest a reason why using a conical flask instead of a beaker would give more accurate results in this experiment for 1 mark. Well, think about it. What is the cotton wool for that we often put in the top of conical flasks? Some people think it's to stop gases escaping. That is a bad error. It's not. Cotton wool is porous, has tiny holes, and those holes are thousands of times bigger than any gas molecule. So gas molecules can freely move out through the cotton wool. They may be slowed down, but they can freely move out. So what's the cotton wool for? Well, any acid that spits up and hits the cotton wool, remember, we're assuming any change in mass is due to CO2. So any acid that spits out during the reaction, we're going to think and record that as CO2 lost when that isn't the case. So it's going to affect the accuracy of our results. So that cotton wool is there to trap any acid that spits out, and therefore that mass will not be lost because, of course, the cotton wool with acid is being measured by the balance. Now, just imagine you try to do this with a beaker. For a start, you probably can't put cotton wool across the top of a beaker. And a beaker's a lot wider, so you're going to get a lot more acid lost. The shape of the conical flask, the fact that it's got those sides slanting up, means any acid that spits out might not even get to the cotton wool because it will hit the side of the flask and run back down like my crazy D-grade GCSE art drawing shows. Whereas a beaker is much more open at the top, easy for acid to be lost, almost impossible to put cotton wool across the top of the beaker without it falling in. Our conical flask, therefore, is superb. All right, let's put that answer down. Okay, so the answer to 1.1 for 1 mark. Conical flask is shaped to prevent the loss of reactants, which would affect the mass, and therefore affect our accuracy. The cotton wool can be put at the top of a conical flask. It can't be put at the top of a beaker, so we get a reduction in the loss of acid during the experiment, making it more accurate. Now let's move on to question 1.2. So let's look here. Okay, we need to use figure 2 to calculate the rate of reaction at 2 minutes. Deduce the units of your calculated rate, and this is worth 3 marks. Okay, let's get into this. I'm going to zoom in a little. So let's have a look here. 1.2. Use figure 2 to calculate the rate of reaction at 2 minutes. Deduce the units of your calculated rate. So at the bottom, we've got rate and units written, and this is worth 3 marks. So we want to go along at the bottom to where it says time, and then we want to go to 2 minutes and follow the line up to where it meets the curve. Now, because we're not dealing with a straight line, we can't just take the gradient of the straight line of the fastest bit. If we were doing the initial rate of reaction, we could take right at the start the straight bit. But here, we've got a bit of a curve going on. So what you're going to do is, first of all, mark out at 2 minutes. So you can see it's about a mass loss of 2.1. And what we want to do, and I'm not very good at this, but we want to make a straight line. That's not good enough. This is a tricky bit. You've got to make a straight line through that point that touches both the top of the graph and your y-axis. Okay, so you can see I'm struggling here on the computer. It's a little bit difficult. If you've got a ruler, a little bit easier. How do you know when it's done right? Visually, no, it's never going to be quite as accurate as I can get it here, but that's about as good as I can get on the computer, it's obviously a bit easier with your ruler because you can just alter that a lot easier. Now what we want to do is draw any triangle going across. I'm trying to make the units nice for myself, okay? I'm trying to make it nice. So we're doing a tangent to the point. Make sure it touches both the axes. Make sure the space visually around each side of that line is equal. I've not done it too well. You can see the triangular space at the bottom is a little bit smaller, but it's going to come out roughly right. So now the gradient of that little tangent I've drawn is going to be equal to the rate of reaction at exactly 2 minutes. So I'm basically doing y over x here. So going up on my y-axis, I can see I've got 10, what's that, 11, 1.1, I've got like 11 little squares, maybe 1.1 to 1.2. I'm going to call it 1.1. And then along the bottom here, we've got, let's see, 10 little squares, 21 little squares. So that's going to be 2.1 along the bottom. So I'm going to do 1.1 divided by 2.1, which is y over x, and I'm going to get 0.524. Now, in the mark scheme, they allow you anywhere between sort of 0.45 and 0.55, something like that. I'm not really sure, but it's roughly in the right area. So slap that down as the answer, and now we just need to work out the units. Well, we look at y and it's grams, we look at x and it's minutes, so it's grams per minute. Now GCSE, you can put the diagonal line grams per minute, but at A level you need to put G to the min to the minus 1. Okay, so 1.1 over 2.1, 0.524, and that's grams per minute. Awesome. Let's move on to 1.3 and see what they're going to ask us there. Sketch on figure 2 the curve you'd expect when 25 centimeter cubed of a 2.23 mole per decimeter solution of chloroethanoic acid reacts with an excess of sodium hydrogen carbonate. Suggests why chloroethanoic acid is a stronger acid than ethanoic acid. So we've got 3 parts to this question. We need to start with a sketch and then finish with a suggestion and a written answer. Okay, let's get into it. Okay, let's do this. 3 marks. So something to notice here, checking out the graph. Figure 2 shows the results of this experiment when 25 centimeter cubed of 2.23 mole of ethanoic acid reacts with an excess of sodium hydrogen carbonate. So what we can tell from this is that actually the moles are equal. So because N over CV, right, the concentration and the volume are equal for both the chloroethanoic acid and just the ethanoic acid, which means we've got the identical amount of moles of both acids. So we're told the chloroethanoic acid is stronger, which means it's going to dissociate more fully, releasing hydrogen ions faster. So it should react faster, the chloroethanoic acid. But the fact that they have an equal amount of moles means that the total amount of carbon dioxide that can be released should be roughly the same. So what I need to show on this graph is a faster rate of reaction but ending at the same mass of CO2 released, i.e. the same amount of product, because we've only got the same moles of reactant. So let's show that on this graph. And so your 2 marks are going to be for drawing a line that's steeper and to the left, so showing that it's releasing CO2 in a shorter amount of time, although it shouldn't go above that line. That would be bad. I keep going above the line. I'm so rubbish at drawing hands-free on this thing. Right, so it's got to come up here and then finish to show the same amount of CO2 released. There we go. All right, and that will get you both marks. So a steeper line to the left, finishing in the same place as the other acid. Now for the final mark, we really want to look at why is chloroethanoic acid stronger than ethanoic acid? Well, what's the only difference? Well, chloroethanoic acid has a chlorine atom. So here's ethanoic acid. See, it's got the OH bond, and it's really about this OH bond over here. How easy is that to break? Well, obviously the electrons are pulled slightly towards those oxygens because they're electronegative, but guess what? Chloroethanoic acid has a chlorine atom, which is also electronegative and electron withdrawing. So the electron cloud across the OH bond is going to be drawn towards that chlorine atom. This is going to further polarize the bond, increase the delta positive on the hydrogen, and therefore weaken the OH bond, the oxygen hydrogen bond, or hydroxide bond, the alcohol bond, whatever you want to say. So it's more strongly polarized, weakening the bond, easier to break. Therefore, it's going to dissociate more fully, releasing those hydrogen ions and reacting faster as an acid. So chloroethanoic acid is going to be a stronger acid, as that bond is more easy to break. It's going to dissociate faster than ethanoic acid. And here we go.
You're still here? It's over.